realize that pH plus POH still equal to 14 whenever we're dealing with it within our system. So let's define what is a buffer, right? And we're going to take a look at how to create a buffer. So buffers maintain relatively constant pH, even with addition of acid or base to solution. Generally, most buffers consist of a weak acid and equal amounts of conjugate base. The equation that governs buffer titrations is called the Henderson-Hasselbalch equation, where it states that pH is equal to pKa plus the log of conjugate base all over acid. The way I remember this equation is I think of it as pH is equal to pKa plus the log of AHA, right? So I always make sure that it's conjugate base over acid. So the A, Ah, and then Ha. So that's how I still remember that it's conjugate base over acid instead of acid over conjugate base. Okay, for your Henderson-Hasselbalch. This is an equation that you're going to be using whenever we have a buffer situation. And this is generally for any, is it possible to do that equation with POH? It's just 14 minus whatever the pH is. So you can solve for pH and then you do 14 minus that and you'll get POH. Okay? So it's typically some acid versus some hydroxide, giving you conjugate base plus water. Does that make sense for everyone so far? What we covered? All right. So let's take a look at buffer ranges before we actually talk about making a perfect buffer. So these are all the ranges, and this is how you can actually add so much acid or base to a solution and not have it change. So, sure, I can go back for a second, no worries. So it's how much conjugate base do we have relative to the acid that's in solution as we add some base to some weak acid. Or, yeah. Because buffers only form when we start with a weak acid. No problem. Thank you for letting us know. You need to go back. So buffer range of concentrations. If we're looking at the concentration of conjugate base relative to the acid, if it's 1 to 10, your equation is going to be pH is equal to pKa plus log of 1 over 10, which is simply pH is equal to pKa minus 1. You can. So someone asked on they had a question. Can you do POH is equal to pKb plus log of conjugate acid over base? You can, but typically you always start with an acid and you're adding base to the system. Meryl, if you email me, I have a PDF of my slides and I can send it to you after lecture. Email is khoin79@yahoo.com. That has been clearly made. I've announced it multiple times in class. If people want the lecture notes and slides, feel free to shoot me an email. Only like 5 people have done that. So you want it, email. pKa minus 1, right? Now, if it's 100 times the other way, where it's 10 times the concentration of conjugate base to 1 of acid, that's pH is equal to pKa plus log of 10 over 1, or log of 10. That's just 1. So pH is equal to pKa plus 1. So what you notice is that the buffer ranges for concentrations are what we call a buffer. It's always pH plus or minus 1 for all buffer concentrations. Okay. And that's pretty key because that's typically what the ranges are for what we consider a buffer. And we'll look at it on a buffer titration curve and you'll see where the plus or minus 1 comes into play. Okay. So let's take a look at a question dealing with buffers. So first question of the day. Our acid, which is a weak acid, has a pKa of 4.7. No worries. Going back one slide. It's plus or minus 1 for all buffer concentrations. 1 over 10 is 10 to the negative 1. Just bring out using the exponent power. That's how you get minus 1. And the other one is 10 to over 1, which is log of 10, which is the identity rule, which means it's just itself. So it's 1. Cool. Just in case like people forgot the log rules that we went over last week. So let's say we have a weak acid. Remember, weak acids have pKa's between 0 and 14. And since this pKa is around 4.7, we know it's a weak acid. Which buffer would create a solution buffered at a pH of 5? Answer choices are as follows. 1 equivalence of acid to 1 equivalence of conjugate base. You can think of it as like 1 mole versus 1 mole. B, 1 equivalence of acid to a half equivalence. I'm just going to simplify down to of conjugate base. C, 1 equivalence of acid to a third equivalence of strong base, and D 1 equivalence of conjugate base, and we have a third equivalence of strong acid. So, which one will give us a pH buffered at 5? So we're using our Henderson-Hasselbalch and trying to find a concentration ratio of conjugate base to acid that will give us our 0.3 difference, right? Because we know pH is 5, pKa is 4.7. The log of conjugate base to acid is 4.7. Sorry, I'm just typing up for people who are asking questions. We know pH is 5. We know pKa is 4.7. Okay. So we do the math. We see that 0.3 is equal to log of conjugate base over acid. But we know what log of what equals 0.3. Good. Everyone knows log of 2 is equal to 0.3, right? From our useful logs, which means what? Conjugate base over acid has to equal to 2 to 1, right? There has to be twice as many conjugate base as there is to acid. So A is 1 to 1, right? This is 1 conjugate base to 1 acid. That's no good. Let's look at this one. This is 1/2 to 1. So it's just 1/2. That's not 2 to 1. That can't work. This one, we actually have to do out, right? So we have acid and we're going to add hydroxide. That's going to yield us strong acid, so it's one-way arrow basically. It's going to yield us conjugate base plus water, right? If we have 1 mole's worth of this and 1/3 of this, right? Strong base is going to rip off every acid available. So we're going to, and this is 0 and 0 to start. Think of doing your ice box for equilibrium. This is our initial conditions. Our change is going to be minus 1/3, minus 1/3, add 1/3, add 1/3, right? So then equilibrium, you're going to have 2/3 of the conjugate acid, the acid, and 1/3 of the base. So 1/3 divided by 2/3 gives us 1/2 again, which doesn't work. So by process of elimination, we should be able to get the last one and assume that it's right, but we should do our due diligence and check using our equilibrium and icebox. So we're starting with the conjugate base and we're adding acid. That's going to form our acid and some water, right? So we start with 1 mole's worth of that and 1/3 moles of this. That's our initial. This is 0. This is 0. Our change is going to be minus 1/3, minus 1/3, add 1/3, add 1/3. And then equilibrium is going to be the difference or sum. So it's going to be 2/3 conjugate base, 0 of the acid left over, and 1/3 of our 0 of our acidic water or hydrogen plus limiting reactants, Michaela. The reaction can only go as small as the thing that limits it. You can't subtract 1 from something you don't have, right? So if we do our conjugate base over acid relationship, we're going to get 2/3 of a mole over 1/3 of a mole. That's going to be a 2-to-1 ratio. So this is the correct answer, okay? So we got to make sure that we understand how to use Henderson-Hasselbalch, and you begin to see why I make you guys remember those log rules and that log review that we did all that time ago. Does that make sense? Let me know if I went too fast for anyone. Kind of crucial. Henderson-Hasselbalch. Pretty important for buffers. Cool. Okay, so let's keep on going. Let's talk about how to make buffers. So we're going to look at buffer recipes. And realistically, all we're trying to do is make equal concentrations of conjugate base to acid, right? Where you pull off half of the hydrogens that are on the acid, okay? This is for a perfect buffer solution. So this is equal concentrations of acid to equal concentrations of conjugate base, okay? Number 1. Mix equivalent amounts of weak acid and its conjugate base. So good example of this would have been your HCO2H or acetic acid, and you have some sodium acetate, right? HCO2. Equal amounts of each. So you have your acid. This is what I consider HA. This is what I consider A minus, right? Because this thing is the minus, this is the plus from the sodium in solution. So equal amounts of those. So when I say HA and A minus, it could be for any type of acid, any type of conjugate base available to it. I like being general because then you can use it in like your biochem situations as well. Okay. And your situations in the human body, like you think of carbonic acid, right? The other way to make a perfect buffer recipe, we mix 1 equivalence of weak acid plus a half equivalence of a strong base. So weak acid and a strong base. So if you think about it, you start off with 1 moles of weak acid and half a mole of strong base. You're going to get some conjugate acid plus water left over, right? So we subtract 0.5, 0.5, add 0.5, and then this is 0.5 as well. You're going to end up with equal concentrations of acid and equal concentrations of base, conjugate base. Okay. Strong base will rip off every hydrogen available. Great example of this. Acetic acid plus KOH, right? Next way to make a buffer, we're going to mix 1 equivalence. Sorry. There you go. I just gave examples of real life things that you can actually mix together. But yeah, 1 mole of this and half a mole of the KOH, right, in your system. The third way to make a perfect buffer is to mix 1 equivalence of weak base plus a half equivalence of strong acid. Okay. If you think about it, here's our weak base plus our strong acid. It's going to give us our conjugate acid plus water, right? So 1 mole of this, half a mole of this, subtract half a mole, subtract half a mole, add half a mole, add half a mole, sorry, 0.5. So you have 0.5 conjugate base and 0.5 of your acid again. This will be 0 acid left over, and you have half of water, half a mole's worth of water left over, right? Equivalence is just like, think of it as just equal equivalent amounts ratios with the other thing. So if I'm adding like what I call one equivalence, it could be 1 mole versus half a mole. It could be 2 moles versus 1 mole, right? As long as it's a 1-to-2 or 2-to-1 ratio of your weak acid or weak base to strong acid relationship. So saying you have one equivalence of something and half equivalence of the other. This handles all the situations: molarity, molality, normality, all of those. That's why I like writing equivalents, right? Because those are all the ways you can get concentrations, right? But you're just trying to do a ratio of like 2-to-1, 2 parts of your weak base and 1 part of strong acid, right? If you think about it like in a recipe. In terms of molecules. That's how I like to think of it. This is also how I break down like baking, and if you're doing like mixtures for chemistry and stuff like that. I never bother to do the exact moles amounts unless like it's absolutely necessary for that type of reaction. And with baking as well, you can get the ratios correctly and you can totally do it. Okay, sorry. Oh, so I was asked to slow down. I did. I just didn't bother to carry the work down. I did add 0.05 moles of water on the second one. I just didn't carry the work down because what we care about to make a buffer is to have equal amounts of conjugate acid to conjugate base. And I just wanted to show that the conjugate base to conjugate acid was 1-to-1. There was a question that was like, why didn't we add 0.5 moles of water on number 2, but we did for number 3? We kind of did. I just didn't write it down because water's there. It's in solution. We don't need to really carry on that work. But the key part is showing that you have an equilibrium, right? Because this is our typical ice box. By the way, I stands for initial. C stands for the change. And E stands for equilibrium. In case you guys never had to do an icebox before. But that's what's happening in a chemical reaction, especially having to deal with equilibrium. So this is why to make those buffers and stuff like that, you usually have to come in way the heck before chem lab to do it. And this is what your TAs had to do for you guys when they were doing buffers and buffer solutions for you guys. TAs have to come in and do that chem prep mixture for you guys when you had to do Chem 1A lab for this stuff, for buffer titration. Does that make sense? Sorry if I'm going too fast. We have time. Number 4, the fourth way to make a perfect buffer solution. Well, yeah, I do have to say bless those chem TAs. They definitely don't get paid enough. So you get mix 1 equivalents of weak base plus the conjugate acid. Ew, that's no good. This is also, you're getting like graduate students to do the work, right? They're getting paid what? I remember being a TA and we got a stipend of $2,000 a month to do everything. So hence why chem TAs hardly put in any work to being a chem TA. I just feel bad for grad students. You're working for slave wages. If you think about how many hours you put in a week plus how much work that is needed to be done and how much they're paying you, like it ends up being a little bit better than minimum wage. And minimum wage back then was like $7 an hour. It was rough. So mix one equivalence of weak base and one equivalence of its conjugate acid. Okay. Perfect example of this. Here's our weak base. Here's our ammonia, and then here's your ammonium chloride. So this is also how you create another stable buffer solution. So I've given you 4 examples of how to create a stable buffer solution, all of which lead to a 1-to-1 ratio of conjugate base to acid in your solution, or acid, one equivalence of weak acid to one equivalence of its conjugate base. Okay. So with that, what do we notice? We're generally working with things that are weak when we're getting a buffer solution. So we need to remember 2 equations, the weak acid only equation and the weak base only equation. So weak acid only equation, where pH is equal to 1/2 pKa minus 1/2 log of HA. And I used to love this equation. You can't tell me enough how much I don't love this equation. It's so awesome. It saves me so much time. So this equation, I would love doing every time I have a multiple choice test. The reason being, because I don't have to show my steps. Because if you think about it, if you were given some pKa, in order to find the pH of it normally, right, you would have to go pKa is equal to negative log of Ka. Then we know that Ka was your hydronium plus your conjugate base all over your original acid, right? And you would use that, and then you would then so you would use pKa, find Ka, then find Ka to find your hydronium concentration, and then then you would have to take it and plug that hydronium concentration to negative pH of log of your hydronium. Pain in the rear. This equation handles all of that. So much easier to do. I'd literally like just 1/2 pKa minus 1/2 log of my initial concentration. Done. I'm off by like 1,000th or 10,000th of a decimal place. And that's it. So in terms of sig figs, I would be pretty good for pH. So this equation is huge, right? Otherwise, you'd have to go from one step to the next step to the third step. Does that make sense? This is what you had to do before when you were doing like chem FRQ type questions. You had to show all the work. But the weak acid equation bypasses all of that. Saves me so much time. And what it is just the algebraic manipulation of using all those 3 steps together to solve for pH. Okay? The other equation that we want to know is the weak base only equation. So whenever we have a weak base only, we get POH is equal to is equal to 1/2 pKb minus 1/2 log of the base. This is when pKb is between 0 and 14 as well. So these 2 equations are lifesavers on your MCAT or any type of multiple choice dealing with weak acid, weak base, or any type of buffer type situation. Okay. Any questions? So far, the only three equations that we had to know were Henderson-Hasselbalch, pH is equal to pKa plus log of conjugate base over acid, and your weak acid only and weak base only equations. Okay. Everything up to now we were just doing by doing equilibrium. Any questions so far? Okay. So let's take a look at neutralization. Neutralization is mixing equal amounts of acid to base. And titration is quantitative addition of acid to base or base to acid that's what titration is, right? We're slowly adding it in. This is the lab where you had to add things in drop by drop, really, really slow. And if you got impatient, then you had to start all over again. This was a little painstaking. Remember, you had that nice burette, and then you had to have the little valve, and you had to go drip, 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 right? This is that lab. That's titration. Quantitative addition of acid to base or base to acid. Because they don't tell you what you have in the thing, and they don't tell you what you're adding to it, right? Or they usually tell you one or the other. They tell you the concentration in the burette or the concentration in the beaker that you're collecting that drop to drop in, okay? So let's look at some titration curves. And so these are some of the things that they can do with regards to titration. So with titration curves, the first type of titration curves is the strong acid, strong base relationship. So y-axis is the pH of the solution. And the x-axis is milliliters of, let's say, hydroxide added to solution, commonly called the titrant. So the thing in the burette that you're dropping down, right? And the acid is what we start with in the solution. So if we have a strong acid, what's the pH for strong acid? Yeah, something really low, right? So let's start really low. As we add more and more base, doesn't really change the pH all that much till it all of a sudden it just changes really quickly. And at this point, this is around a pH of 7. So this point is commonly referred to as the equivalence point. Endpoint or neutralization point. Right? This is when we have equal moles of acid to base, right? And then if we keep on adding base, then you're going to get something that's fairly basic, right? Because this is just going to be all OH minuses afterwards, okay? Hence why high pH. So if we're looking at what equation we should be using where, right? At A, we mainly have what? Strong acid, right? So we should be able to find the pH as simply the negative log of your strong acid. In this case, whatever the strong acid is. At B, this is your equivalence point. So we know pH first between a strong acid and a strong base. One wants to get rid of everything and the other one wants to scoop them all up, right? They all want to get matched up and paired up so they neutralize each other out. pH is 7. And afterwards, we continually add OH to the system. So you'll only have OH in your concentration, then you'll get a POH of the concentration of your hydroxide that you had added in. How many moles per liter that you added in additional, right? Based on where you're at here. And your concentration of your original titrant. So your strong base, basically. Okay? Just in general. Any questions between your strong acid, strong base? This is the simplest titration curve that you can have. Highly doubt that this was what you guys did in chem lab. Maybe in high school. Right? Strong base, SB. So SA is strong acid, SB is strong base. OH is considered a strong base. And H3O plus is considered a strong acid, right? That's just a bunch of H pluses floating around in water. The other one is OH minus, means that there's a lack of H's. So that solution is ending up to be basic. Based on our definitions from last week from acid-base chemistry. So these are the equations that we should be looking at any given point, okay? The main titration curve that you end up looking at the most is your weak acid, strong base relationship. So this is a weak acid, right? Weak acid, non-protic. So when we graph it on your titration curve, this is pH. Doesn't start that low. This is ml of O minus, your titrant. And then has this curve. This is commonly referred to as the lip of weakness. It doesn't dissociate, non-protic by itself. That's what non-protic means. It has this lip of weakness. So this curve here is what we call this lip of weakness. And it's going to level off. Then it's going to curve up. And then it's going to look like this. So at this halfway point, this is called the half equivalence point. Right? That's when you have equal amounts of conjugate base to acid for that weak acid, or half equivalence. This is when you ripped off half of the hydrogen. So if you think about it, at this point, we have all HA. At this point, we have equal amounts of HA to A minus. And at this point, we call this the equivalence point. This is all A minus now. So do you see what's happening? As you add OH to the system, the strong base, it's beginning to rip off every hydrogen available to your weak acid. But during this region here, where it's kind of flat, we ended up calling this the buffer region. Hence why we spent all that time going over buffers earlier. So if we labeled this A for the starting, B for this whole section, C for the equivalence point, and D for when you're somewhere up here, let's look at what equation should we be using. So when we're at A, we just started, we haven't added any hydroxide or strong base to the situation, so we only have a weak acid. So what equation should we be using to find the pH? It's only 3 equations we learned today. What do we have only at the beginning, at A? Do we have strong base? We have acid. What kind of acid? Strong or weak? Weak. So what equation should we be using to find the pH of that acid? Yeah, the one with 1/2 in it. Yes, the weak acid only equation. pH is equal to 1/2 pKa right here minus 1/2 log of your concentration of your acid. Let me write that better. That you had in your solution. Okay. During the buffer region, what equation should we be using to find pH? There you go, Henderson-Hasselbalch. pH is equal to pKa plus log of conjugate base over acid. At C, what do we have? What are we left with, right? Because up to this point, we've been adding more and more OHs, and it's been ripping off more and more H's. So what are we left with at C? It's not a, remember, we got to be careful. What's the conjugate of a weak acid? We learned this last week. Weak base. Not a strong base. So be careful, Dominic. Yes, contrary to popular belief. Everyone always thinks that it, yeah. So be careful, because if you use a strong base, then you want to use POH is equal to negative log of OH, right? If you're saying it's a strong base. But if it's a weak base, then we got to use the weak base equation. The other 1/2 equation. 1/2 pKb minus 1/2 log of your, where did I write strong base? Oh, you're adding, this is the strong base right here. But at this point, this is just barely neutralize all the H's. I'm going to draw it in red. This is the strong base that I've added to the solution, the OH. Right? So OH at that point has slowly ripped off an H until it got to here. And at this point, we know that we only have A minus left, right? So this is a weak base or conjugate base that's around. Because OH has been neutralized by all the H's at C. Does that make sense? So that's why we're still having our conjugate base, not our OH. So be careful. Because what is the OH doing? It's ripping all the hydrogens, right? This is like being in New York, right? You go there, there's like more women to men. You're all the guys, all the lovely couples are gonna get broken up. You know, all those A-type personality women, just gonna like get all your men away from you. So that's what's happening, right? Your strong base is gonna rip off every hydrogen available. Correct. So D is where the strong base is, right? Because at this point, now all you have is no more acid. And what have you been adding? Conjugate. Oh, there's a strong base. So at D, Sophie's correct. Your POH now is simply negative log of your strong base in your system. So this is where you use it, Dominic. Strong base. Okay? Because the strong base is actually the OH minus that we've added to the system. But up to that point, it's been saturated, right? Every strong base that we've added has went and grabbed the hydrogen from the weak acid, right? We got these shaky relationships. They're just coming out of high school. They're fragile. They meet these like young 20-somethings that are like, there's not enough guys in New York. I need a man. And they pluck them right off, right? But they can only take one at a time, right? So that's what's happening with your strong base ripping off every hydrogen to the certain point when we get to equivalence point, right? And at equivalence point, now there's no more hydrogens around for it to be plucked off. So what we add further only goes past that equivalence point. So if you were doing this in chem lab and you were doing a titration and you added all this extra MLOH, well, your solution is now ruined, right? This is why your teacher's like, start over. Because now all you have is OH minus in your solution. And you can't find out where the buffer was, and you can't find out where equivalence point was, and all that stuff, right? Does that make sense? This is why you can't just like open that burette and just let all that drop down. Okay. Any questions? Cool. So now let's take a look at our weak base with strong acid addition. So same thing is happening. We start with a weak base and we're going to add a strong acid. And along the way, we get a buffer somewhere in between and we get the full change across the system. So this is still pH. Now our titrant that we're adding is our strong acid, some hydronia. So we're still going to have our lip of weakness. It's going to have this little flat region. Then there's another slight change, and then it'll level off again. Okay. This is still A. This is still C. This whole region, we're still going to call it B for buffer, and then we're going to end up with some D, right? Some relatively strong acid at the end. So at A, how will we calculate pH? What do we have there? What are we starting with? Start with a weak base. So what equation should we be using if we only have weak base at the beginning? Yep, the weak base equation. Yep, so POH is equal to 1/2 PKB minus 1/2 log of your weak base. Then this whole region at B, we have a buffer again, right? So we're going to use our good old friend, the Henderson-Hasselbalch equation. Conjugate base or base over acid. Still looking at the same thing. At C, now every base that we had has an acid added to it. So we only have solely weak acid in solution, right? So we should be using the weak acid equation, 1/2 pKa, right? Minus 1/2 log of the new acid that we formed, HA, in our system, whatever the weak base was that we had to start with. And last but not least, if we're at D, we solely have acid, so it's going to be negative log of your strong acid in solution, right? Any questions? Okay. So we've covered the two major ones, the weak acid and strong base addition, and the weak base and the strong acid addition. Keep in mind that we can also have polyprotic acids where you have multiple dissociable protons. Think of your carbonic acid, sulfuric acid. Think of your phosphoric acid, right? H3PO4. Those have multiple dissociable protons that you can have in solution. So, by the way, how did you know when you got to equivalence point, by the way? When you guys did this titration lab? What would happen? You get a color change. Turn pink, turn blue, turn green to yellow, whatever, right? That you had in your system. How did it do that? So let's take a look at what we call indicators. And indicators themselves are weak acids that are getting titrated at the same time. So let's take a look at what we call indicators. Cool part about indicators. So indicators are used to find the endpoint of titration, right? So what an indicator is, it's a weak acid. Indicators are weak acids. Right? So if it was an indicator H+, it'll give you some type of yellow color, right? If it's an indicator for some base, give you some red color. But what these weak acids do, they give you a color estimate of the pH of solution, right? And they'll bounce back between two colors, okay? Realize that, look, for your indicator, if your pH of the solution is greater than your pKa of your indicator, then the indicator is going to be deprotonated. No. They'll tell you the color schemes that they have for your MCAT. They usually give it in a chart. You don't have to remember specific indicators. You can, but you don't really need to for your MCAT. So if the pH of a solution is less than the pKa of your indicator, it's going to be protonated. And it changes color. So then there's a color change between the two, right? So usually the endpoint of titration is when the pH is equal to the pKa of the indicator. So when you're doing a lab, you actually have to know what pH you're going to end at. So this is what the TAs are actually calculating for. And they have to generally set it up by themselves. Most professors really don't give them any playbook or handbook on how to do it. So the endpoint of titration is when the pH is equal to the pKa of the indicator, right? And so that, what does that mean? That is when you're reaching half equivalence point for the weak acid of the indicator, right? Remember that point right here in the buffer region? Weak acids themselves, or the indicators themselves, actually have a buffer themselves. So just imagine here's your regular titration curve, and this is your equivalence point. Well, this is the half equivalence point for that indicator, right? So this is when your pH is equal to your pKa, right, of your system. And that is when your concentration of your acid equals the concentration of your conjugate base. Because we know log of 1 is 0, right, in Henderson-Hasselbalch. That's how I know its pH is equal to pKa. So if we use Henderson-Hasselbalch, this is plus log of conjugate base or conjugate acid. The only time when the log region goes to 0 is when the ratio is 1:1. So that's at the half equivalence point. Half equivalence point of the indicator. Okay. Cool. Okay. Any questions on this? So this is how we determine when a buffer titration ends. So let me pull up my acid base equation that I'm going to share with you. I'm going to do some worksheets, questions on it. I can't scroll up, apologies. It actually says 1/2 equivalence point of the indicator, and at that point, the concentration of HA is equal to A minus. This is the thing that I wrote at the bottom. They're equal to each other. It's a 1:1 ratio at that point. Yeah, I totally understand. Sorry, someone said they couldn't see the bottom, and I'm pretty sure that's the case if you're using a desktop to do your Zooms meetings, and that little Zoom scroll bar on the bottom kind of like blocks it out. Okay. So let's take a look at some polyprotic acids and the titration curves. Then we'll also take a look and do some practice problems dealing with buffered titrations. Okay. Yep, definitely going to do that. That's what I'm doing now. So I'm going to share screen. So this is your typical titration curves. This is in your handout, but the ones I want to focus on are the polyprotic acids, right? So here you have 2 weak acids in a row. So this portion right here, I'm going to just do it in red so you can see, it just shows up better. So we're looking at the diprotic acid titrated by a strong base. So here you have 2 protons being ripped off. So this is, you start with H2, then it becomes HA minus. So H2 at the beginning, at this point, then at this point, the next point, it becomes just simply HA minus. And at the second equivalence point, it's simply A2 minus, right? Whatever the conjugate base is. So a perfect example of this would have been your carbonic acid, right? H2CO3. So it starts off with H2CO3. You reach half equivalence points. You have equal amounts of carbonic acid and bicarbonate. And then if you keep on adding strong base to it, it becomes simply bicarbonate. And if you continually add base to it, then you're going to get to the point where you ripped off half of the H's. So now it's equal amounts of bicarbonate and carbonate at the pH is equal to pKa2. And then eventually, if you keep on adding strong base to it, it rips out all the hydrogens, and then you're only left with bicarbonate at A2 minus. Okay. Same thing occurs if you have 3 polyprotic acids. Think of your phosphoric acid, H3PO4. A minus being the phosphate group, right? And A minus, A3 minus is the phosphate group, right? And the 3 hydrogens are each of the hydrogens that you have in your phosphoric acid. Know that your first equivalence, second equivalence point is simply the average of the pKa1, pKa2s. And then for the second equivalence point, it's pKa2 and pKa3, right? So you're thinking about it, it's just the average. And the plus or minus 1, so this is your pH, then you have a plus or minus 1 buffer top and bottom, right? Plus 1 or minus 1 during that buffer range in our system. Now, if we look to the diprotic titrated by strong base with the first proton being strong, right? So look, we have a strong acid relationship here, right? Something that's super strong. Think of sulfuric acid, right? H2SO4. We're going to titrate it. This first interaction is a strong acid, strong base relationship, right? But the second interaction of ripping off the H from the HSO4 minus is going to be a weak interaction. So then it looks like it has that lipo weakness right here, and it still goes through a buffer region. Okay. And this is the last graph here is when you have a strong base that can handle 3 protons. It's the reverse of it, the other case, right? Think of that phosphate group grabbing back those hydrogens that it lost. Okay. So let's do some practice. So question number 1. What is the pH of 0.3 molar of HCl? Let's calculate it. Comments. Remember to write that in scientific notation. That's 3 times 10 to the negative 2. Then you can take the log of it or negative log of it, and you can calculate for everything. This is all last week's stuff, right? So first of all, what is HCl? Strong acid or weak acid? Good. Everyone remembers from last week that it is strong. This is the divorce relationship. I do not want you, and I'm going to make everything H+. This is salting the earth. So if you think about it, this is a strong acid, so we're going to use the pH equation, right? Negative log of your H+ concentration, or your HCl concentration, basically, right? So that's going to be negative log of 3 times 10 to the negative 2. Log product rule tells us what? That's going to be negative log of 3 added to negative log of 10 to the negative 2, right? Log of A times B is equal to log of A plus log of B. So this is going to become 2, right? I can bring that negative 2 to the front. Negative 2 times negative 1 is 2. Log of 10 is just 1. What's log of 3? We should know that from our logs that I gave you. Close, Glenn. But it's a specific decimal number. Yes. Thank you. That's going to be 0.48, and that's negative. So 2 minus 0.48 gives us an answer of 1.52. So for those who chose B, good job. Let's take a look here. What's the pH of 0.1 molar of HF? So first of all, you have to ask yourself, what's hydrofluoric acid? Weak acid or strong acid? Yay, I'm so proud. You guys still remember the weak acids and strong acids. Also, the hint is pKa is between 0 and 14. So we have a weak acid. So what equation should we be using? We have an equation for it, right? You like to call it the 1/2 equation. It's a weak acid equation. So use it, plug it in, tell me what you get. I'm going to give everyone a chance to build those neural pathways themselves. Giving you guys proof that you guys can do this on your MCAT on your own. All right, we have our weak acid only equation. So what's half of 3.3? Mathematically, what's half of 3.3? Thank you, Glenn. 1.65 log of 0.1 is log of 10 times 10 to the negative 1, right? Or actually 1 times 10 to the negative 1. Log of 1 we know is 0. So what's log of 10 times to the negative 1? That's just negative 1, right? So this whole thing is going to become negative 1 times 1/2, negative 1/2, or minus 1/2. So then 0.65 plus 0.5 gives us what? 2.15. Leading us to this answer choice. Any questions on that? Okay. So now we have a pH. I'm trying to find the pH of something that has a concentration of 0.07562 with a pKa of 3.642. So we know pKa is between 0 and 14. That's a weak acid. So we need to use the weak acid equation. Or if you just look at the structure, you see that that is acetic acid. We know that's vinegar. So we also know that's a weak acid by looking at structure as well, right? Besides just giving you the hint of pKa. But once you know that, you can then find the pH of it by using what? Weak acid equation. What'd you guys get? You should know how to work a weak acid equation. The number's a little bit tougher this time, right? It's not as easy. So half of the pKa was 1.821. That's the easy part. Minus 1/2 log of 7.562 times 10 to the negative 2. So we can write that as log of 7.562 plus log of 10 to the negative 2. So this is where we use our approximations, right? We know log of 7 is what? .84. Thank you. So that's 0.84, and we know log of 8. Right? Isn't that just log of 2 plus log of 2 plus log of 2? It's going to be 0.9. Okay. This is going to be -2. So we are somewhere, it's 7.5. So we are somewhere in between 0.84 and 0.9. Let's make it 0.87 for simplicity purposes, because it's like 7.5. Okay. So that's going to be 1.13 negative times a negative a half. So it becomes a positive. So 1.82 plus half of 1.13. Right? What's that going to be? Be 0.56 something, right? 565. And we're going to add it to 1.821. That's approximately 2.3 something. 86. That's pretty darn close approximation to the actual answer, right? That they gave you. Answer choice B. Does that make sense? How are we going to use 1.13? 1.13 is 0.87 minus 2. It's negative. But you're subtracting, right? That's what this negative sign here is. So the negative and negative became positive. So it's like if I added that number after I divided that 1.13 divided by 2. Okay. Let's see if I can find a passage. Give me a second. Okay. Let me see one that I can find that was like a lot of data interpretation for you guys. Okay, let's do this one. One, two, three, four, five, six, seven. Give you guys 7.5 minutes. I'll let you guys go, and then I will come back and go over it. Doing the timer now. Sure. Sorry about that. I'm trying to make sure I can get everything in. I'll zoom out a little bit more so you can actually see top and bottom. There. If I zoom in, you'll get cut off on your screen. That's correct for the person who answered number 7. But keep on going. I'm timing it like a real passage. I will mute that. Thank you. Sorry. I'm just trying to keep the noise off. And relax, I'll add time to it. Said half an I said 7.5 minutes. That was 8 minutes of time. I only went back and forth because the sound for someone unmuted. Okay, let's take a look. That's time. If you didn't finish, we need to get faster. Right? So let's take a look at what you should be doing relative to try to get yourself faster. So it looks like you have 3 acids and you're doing a titration on all of them, right? Data table suggests you have a pH of 2.3 for acid, 6.3 for A, 1 for B, and 4.22 for C, right? Looks like B might be the strong acid in this case. So, and if you think about it, the lower the pH, the stronger the acid, right? From when we start, even if you are a weak acid to begin with, right? So it should be B, A, C in that order. If you just look at the 0 ml titrant line, you can figure that out. So the best answer choice was C for number 7. And where I got that is by looking at these numbers to start with. The lower the pH, the stronger the acid. The higher the pH, the weaker the acid. Just that simple. Okay. What is the concentration of the solution? This is from one of the passages, yes. It might have been shuffled into the book. This is one of the ones that I have separate from the book, but it might have been shuffled into the new printing of the book. So what is the concentration of the strong base solution used to titrate the acids? So if we get to full titration, so what do we start with? We have 0.1 of your acid with 25 mils of it, right? And you're going to end up with 50 mils because they tell you that the endpoint occurred at the same point in milliliters of base added. That's at 50. So we're using M1 V1 is equal to M2 V2. So this is 25 milliliters times 0.1 molarity. We're going to find the new molarity given the milliliters that we have in solution. Because we're trying to find the amount of base. So we divide by 50 and get a half. Half of 0.1 is 0.05. So your base is only roughly that strong in terms of molarity. Okay. What's the pKa of acid A? So if we're looking at the pKa, we remember that during the half equivalence point, pH is equal to pKa. So half equivalence point is half of the 50, or at 25 milliliters for weak acid. And we know A is a weak acid, right? Weak acid, strong acid in our system. Because if you think about it, here's your pKa at those weak equivalence points, because that's your pH. So then by knowing that, we know that it's 4.26. Okay. Just going to erase all the other stuff because that's what I was using to find it. What acid can be classified as weak? We just went over that. A and C are weak. B is strong, right? Because it hardly ever changes for B, and then it goes to 7, right? It follows the strong acid, strong base titration. So what is true when pH in solution for the third titration for C is 7? What is true about the ratio of the weak acid to conjugate base in solution? So if we think about our titration curve, where half equivalence is reached at 7.4, pH of 7.44, because that's when the pKa is for the third acid. At a pH of 7, you're somewhere like right here, right? You're really close to that 7.44. So we know that this side has more conjugate acid than this side has more conjugate base, right? So we're going to have more acid, and it's going to be closer to that 1-to-1 ratio than it is that 4-to-1 ratio or 3.59-to-1 ratio. Sorry. Someone asked for the last question when I did question 8. Was it wrong to turn it into milliliters? But since this is both in milliliters, you're just going to cancel them out, and you're going to end up with concentration. You can spend time to cancel them into liters, and then you can do the same math, except you're going to have to deal with decimal math. That's why for 8, I didn't bother to change them.
Oh, I meant like I didn't even do the equation. I just turned 50 milliliters into liters, and then it just gave me the answer. Was it wrong to do that?
Yes. That is totally not the answer. You got lucky that you did that. You'll end up with 0.05 liters, but the answers is in molarity, right? So
right.
Moles per liter, and that's not what you're supposed to do. You're supposed to use this. This is like moles of acid versus moles of base, right? So you have to do this concentration times volume to get the moles.
Okay, got it. Thank you.
Yeah, apologies. I was just like, when I thought about that, I was like, wait, you don't need to change them.
No, you're fine. Thank you.
Yeah. No, it's just lucky that it ended up being 0.05. That was the case for 50 milliliters. Sorry, there was another 2 questions. Is it possible to have pKa equation here? You can to find the pKa of this, but you don't know the pKa. I guess you can calculate the concentration that you would have at the time. Seems like a lot of work. For number 9?
Yeah.
Okay.
Yeah,
you can technically do it because you have pH, and you can find pKa minus 1/2 log of your original acid concentration. Because you know this and you know this, you can possibly find that. But this was much easier to be found by understanding that titration curve, that at the half equivalence point, or at 25 mils, your pH is your pKa.
Okay, was the concentration of the acid was 0.1 molarity, right?
Yeah, so you have it. It's not wrong. You can totally do it.
Yeah.
To it, right? But that's a lot of work.
Yeah, for sure. Thank you.
Yeah. Right? Here I'm just looking at a table, and here you're doing a bunch of arithmetic with logs. I don't know. It just seems longer to do it that way. But good question. You can totally do it. Okay, let's go back. Sure. Let's go back to M1 V1 is equal to M2 V2, right? So I have 0.1 times 25 mils is equal to M2 times 50 mils, right? And I divide, so I get 1/2. So if we do the math, 0.1 molarity times 25 mils over 50 mils, that cancels out. It's equal to concentration of M2. Isn't that 1/2 times 0.1? So isn't that 0.1 times 0.5? Isn't that 0.05? 5 times 1, 2 decimal places. You can make this in 1 times 10 to the negative 1. 5 times 10 to the negative 1. Isn't that 5 times 10 to the negative 2, which is this number? Yeah. No problem. Number 12. How can you find the pH at equivalence in the titration of a monoprotic weak acid best be approximated? By finding the average, by multiplying 2 times the pKa of the acid? No. By finding the average of the pKa of the acid and the pH of the titrant base. Right. That is correct. So remember when we went all the way right here? So monoprotic. So we did the pH and then the pKa. We would take the average of the two. So it's right here to find the first equivalence point. It's the pKa1, pKa2 over 2, or the pH. So they're saying for this passage, you can find the average of the pKa of the acid and the pH of the titrant to find the equivalence point. So if we graphed it, so this was this point right here, the equivalence point, that pH can be found by taking the pKa divided by 2 plus your pH of the titrant divided by 2. Okay. And 13, the identity of acid B is most likely which of the following? B we know is a strong acid. And it looks like it's monoprotic, right? There's only one strong acid here that's monoprotic. Sure, I can go back to over 11. Sorry. For 13, it's B. Monoprotic strong acid. There's 2 strong acids, right? But only one of them is monoprotic, or 1 hydrogen, right? Both of these are weak acids. That's not B. B we determined as a strong acid because it stayed pretty much level as 1 all the way. All right, going back to number 11. So we know that at a pH of 7.44, that's our pKa, right? That's our half equivalence point. And so anything before that, you're going to have more acid, weak acid, and then conjugate base. And then everything after that, you're going to have more conjugate base than weak acid. So 7 is going to occur before 7.44. So right here, between 10 and 15 mils of your substance. If that's the case, that number is going to be closer to 1-to-1, right? So when we're at the half equivalence point at 7.44, we know that the concentration of acid to concentration of conjugate base is literally 1-to-1, right? And 7's awfully close to 7.44. So I'm going to choose the answer that has the closest number to 1-to-1, where you have a greater amount of weak acid to conjugate base. Does that make sense how I got it? Sure. 13, the identity of acid B is most likely which of the following acids, right? So we have a strong acid for sulfuric acid and nitric acid, and we have, right, think of your excess oxygen count, and we have weak acids for carbonic acid and acetic acid. So we know those are both out because molecule B has basically relatively same pH for long periods of time without changing, which means it's a strong acid. The other thing that we know is that it's monoprotic, right? Because there's no part of it where it begins to behave like a buffer. So it's monoprotic. So there's only one hydrogen. So I'm going to choose the acid that only has one hydrogen. Okay, did that answer your question too, Alap? Okay, number 12. Oh, 1-to-1. So we're going back to 11, then I'll get to 12. Sorry about that. I'll get to 12 next. So 1-to-1 is at this point, right? We're 7. pH is 7 is probably really close to it, right? So I'm going to choose the ratio that's closest to 1-to-1. Like I said, over here we have all conjugate base, acid, and then over here you have all conjugate base. So the ratio of conjugate acid to conjugate base is greater on the left side of that half equivalence point. And on the right side of that half equivalence point, the ratio of conjugate base to acid is greater. So I'm going to choose something that is on the left side because pH of 7 is on the left side, which means the weak acid is going to exceed the conjugate base. And I'm choosing the ratio that's closest to 1-to-1 because 7 is closer to 1-to-1, right? Or 2.53 is to 1 is closest to 1-to-1 out of all the two ratios I have to choose. Does that make sense for number 11? Yes, there's just more acid, right? Because you think about it, to the left side of your titration curve, this was all acid, right? And as we added base, it ripped off acid, giving you some conjugate base. And then at half equivalence point, that's when you have equal amounts of conjugate base to acid. That's what we call the perfect buffer. Cool. All right, so let's go on to 12. Again, how can the pH at the equivalence in the titration of the monoprotic weak acid best be approximated? Ideally, you can just say like weak base equation. But using the numbers that we had, because we know what pKa is of each of these weak acids, right? And I circled it. This is the pKa for acid A, and this is the pKa for acid C. So if we multiply 2 times the pKa of the acid, we know that that's not going to give us because this is pKa of the acid, right? And that's equal to pH here. And we know that at this point, the equivalence pH isn't twice that. So we know that that's not true. If we add 1 to the pKa of the acid, then we're around here, right? Remember, this is the buffer region. This is the equivalence point is definitely outside of the buffer region. Subtracting 3 from the pKa of the acid, that would leave us somewhere down here. That doesn't make any sense. So by finding the average of the pKa of the acid and the pH of the titrant. So we're simply, let me rewrite this because it's kind of cut off on the side here. It's hard to see. So if we do it, this point, the pH at the end is simply pKa over 2 plus pH of the titrant, in this case your base, the average of what we sent. And that point will be your equivalence point at that point. Or you could have just did process by elimination and know that A is wrong, C is wrong, and D is wrong to solve for B.
Okay. I think I was just confused because is this like an equation that we should know, or is this solely because that was
Yeah,
just
if you have a monoprotic thing, you can use it using the pH of the titrant to solve this. This is one of those like those GChem textbook answers. Like you really don't need to do this. Like you could have done it using your weak. You could have did pH is equal to or a POH is equal to 1/2 pKb minus log of your conjugate base at that point. But in this point right now, we don't know what the base was. So we couldn't have done it using that equation that we talked about. Does that make sense?
Yeah, thank you. And
That we
then
would have used
also
before. Sorry, I have to go back.
if you add 1 to the pKa, wouldn't that move it to the right along the curve of the graph?
Yeah, it would move it to the right. But remember
Okay.
the region that we talked about is
Uh-huh.
somewhere in between. Like, so if we talk about it here, God, why is it going up like ridiculous amounts of pages? Okay, so we talk about it like right here. So this is the pH is equal to pKa. So +1 -1 is somewhere like right. I'm gonna do it in red so you can see. So it's like right here and right here respectively, right? This is what we call the buffer region. That's ±1 from the pKa.
Okay, got it. Thank you.
Yeah. So you move it to the right or to the left, right? If it's -1, it's to the left. +1, it's to the right. But we're still in the buffer region, but equivalence point is outside of the buffer region. So that's why you can't use that. Okay? Why that answer is false. Cool. With that said, it's 4:00. If you have questions, I'll be here tomorrow for office hours on Thursday. Otherwise, I will see you guys next week and we'll talk about physics on Monday. Oh yeah. If you always feel like I'm going too fast, always feel free to let me know. Okay, definitely. Yes, I'll try to. Hello. Can you guys hear me? Yes. I don't know what happened. It just like froze on me and then like it died. So apologies, but yes, if I have time, I'm definitely going to try to incorporate more passages then. Not a problem. I was like in the middle of talking about that, and then I was like, it just stopped. Like, and I was like, no, I'm trying to get a point across. But yes, sounds good. We'll definitely try doing that for physics. Got lots of passages. Cool. You too. Have a good night. Thank you.